Hi, and welcome again to my Physics Online video lecture supplement series. In today's video, I'm going to begin a new set of lectures which covers current and resistance. Before we get into the topic of current, I wanted to give a little overview of all this. Basically, what current is it's the flow of electrical charges, and generally this is taken across some potential difference. Usually we do this in the context of a circuit. For example, you have electrons and the positive charge carrier holes flowing in opposite directions along a wire. However, you can also get current as flow from a voltage source to ground. So in a sense, there is electrical current in a lightning strike. We basically are going to look at this in the context of charges moving both across potential differences and also moving along an E field line, or moving in the presence of an E field, I should say. And then in the second part, we're going to talk a bit about what impedes the flow of current in the form of a resistor, and how do we measure the flow of current, how do we measure the potential difference, etc. So with that said, part one is going to be focused just on current. And again, electrical current is the flow of charges. By convention, the way that we define the direction of a current is that it's the direction in which the positive charges are actually flowing. So here you see charges moving in a wire, and this basically is like a section of wire. These are the positive charge carriers, these are the negative charge carriers. And as you know, if you apply an electric field to the wire, what will happen is any free charges are going to accelerate either along or against the field line. If it's a positive charge, it's going to accelerate along the electric field line. If it's a negative charge, it will accelerate against the electric field. So basically, the current is going to be moving in the same direction as the applied electric field. And basically what that means is that we're taking the current to be the opposite of the direction in which all the electrons, which are the negative charge carriers, are moving, and hence in the same direction as the positive charge carriers, which are the holes created in each atom as an electron is pulled from its orbit and moved to the next atom in the chain. The actual charge carriers that are moving themselves are, in other words, the electrons. But as you remove one electron from an atom, it creates basically a hole into which another electron could be placed. And so that atom effectively has a positive charge. And so you have an electron jumping from atom to atom to atom to atom, and the result is that the hole that's being pulled is going to move in the opposite direction. So this electron moves from here to here. That effectively means that the hole has moved from here to here. And before moving on, I should make note of one other thing, which is that typically we talk about current occurring inside of a conductor, like a conducting wire of copper or what have you. And you'll notice that there is an E field, and specifically the E field is inside of the wire. So I bring this up because in our previous discussion we've said there is no electric field inside of a conductor, or so it seems. The way that you reconcile these two statements, the fact that the particles are moving, the charge carriers are moving under the influence of an electric field, with the fact that we've said there's usually not an electric field inside of a conductor, is by recalling that the condition for having no electric field inside of a conductor is that the conductor has to be in static equilibrium. So that's the electrostatics case. That means that the charges are basically not moving. Well, if you have charges which are moving, you're no longer in the static case, and so an electric field is allowed in that case. So that's where the electric field is allowed to be applied. So how do we actually define current a little more rigorously, or give it a more mathematical definition? Well, current is the rate at which a charge flows through a surface of area A. So if we look back on this slide, here's our surface of area A, and basically we just say how many charges move through this cross section per unit time. That is what the current represents. So in the case of current flowing through a wire, as in a circuit, the surface should be perpendicular to the direction of the current, which largely means that it's going to be a cross section of the wire. So if the wire is thought of a very, very, very long, very, very, very thin cylinder, then the easiest surface to deal with is probably the cross section that looks like a circle. With that said, we could take another cross section and still get the same result. So the cross section need not be actually perpendicular to the current. It simply needs to be a single surface and not a closed surface, as in the Gaussian case. The average current then is the amount of charge that passes through that cross section per unit time. So here's the average current, this is charge, this is time. Average current is delta Q over delta T, charge per unit time. And so the unit that we use for current is basically the ampere. And the ampere is defined as 1 coulomb per second. This, of course, is an average current, and we can also talk about instantaneous current, which is basically the amount of charge that's going to flow through the surface in an infinitesimal amount of time. We can define that kind of analogously to the way that we've defined other average as opposed to instantaneous quantities, which is that we find the instantaneous quantity by taking the limit as this delta t approaches 0 of the average. So in other words, if we do this for a short enough amount of time, we effectively have the instantaneous current. The next thing that I want to talk about in this is what's called drift velocity. Drift velocity is a sort of averaged velocity for an individual particle. And what you see here in this diagram is here's an electron, here's the electric field direction. The electron doesn't just move in a straight line against the electric field. It doesn't just accelerate in a straight line against the electric field, for that matter. Of course, if you had initially a conductor in the static condition, where you have equilibrium inside the conductor, and then you apply an electric field, then you imagine the charges, if they were totally free, would be able to move exactly opposite the electric field because they have zero initial velocity, zero initial acceleration. Then you apply a field and the particle begins to accelerate against the field. The truth of the matter is, though, when you have electrons that are placed inside of a conductor, a wire for example, there are other particles nearby with which the electron can collide. And so the electron's actual path might look something like this zigzaggy black line, where it begins to move, it makes a collision, it bounces off, makes some collision, bounces, makes a collision, bounces. Each one of these changes is basically a collision that the particle is making. But if you take the average velocity that this particle has over some long enough time that it's made many collisions, what you'll find is that the particle, even though it's making collisions, even though each collision sends it in a seemingly random direction, even though those collisions may send it in a direction opposite to the E field, it will over time be drifting opposite the direction of the electric field rather than any old direction. So that's what we would expect for a free particle in free space with an electric field. If it is an electron, it should move. If initially at rest, it should move basically against the electric field line. And that's basically what happens on average. And that average is called the drift velocity. So if you average the velocity of this particle over a long enough time, you will find that it is equal to Vd. Delta x over delta t will be Vd. And that Vd, in the case of the negatively charged particle, is in the opposite direction as the electric field line, which is what we would expect. So note that the drift speed or the drift velocity is basically related to the motion of each individual particle. It's, in other words, a microscopic quantity that we're talking about. Current, on the other hand, is a macroscopic or collective quantity. In other words, current has to do with how many electrons move through this cross-section of area per unit time, and also how many holes move in the opposite direction through the same cross-section per unit time. And let's say that we have electrons who have some drift speed Vd, or a drift velocity vector Vd. Then what will happen is, over a sufficiently long time delta t, you get delta x equals Vd delta t. That's just simple kinematics. And within a conductor, there are going to be many charge carriers. Usually we use big N to represent the number, the total number, and we use little n to represent the charge carrier per unit volume. That means how many electrons per, say, cubic meter or per cubic centimeter or what have you. Then you can get the total number of charges in a given volume by multiplying this charge carrier density times the cross-sectional area times delta x, the length over which you're interested. So A delta x is basically a volume term. So we're multiplying a charge density, number of charges per unit volume, times the volume. Therefore, you're getting a number of charges. And so if each of these charge carriers has a charge little q, maybe its little q is about 1.602 times 10 to the minus 19 as per an electron, then the total charge that is basically within a volume, or maybe I should say that passes through a volume, is going to be little q times the number of charges with that little q, which is q in a delta x. So we can put all these terms together. Basically, what we see is the amount of charge which moves through a given region is delta q equals q in a, and delta x can be rewritten as Vd delta t. And if we divide both sides of this by the delta t, you'll get delta q over delta t is equal to q in a Vd. So delta q over delta t is current, and if you take the limit as delta t approaches 0 of this, you get the instantaneous current. So the instantaneous current, a macroscopic quantity, can be related to the drift velocity and the charge of the particles through this equation. I is equal to N Q VdA. And if we're talking for a wire, you can also get the current by using drift velocity times the charge divided by the length over which that charge is distributed. So that's how we relate the drift velocity of an individual electron, because on average all of them will have about the same drift velocity. That's how you relate that drift velocity back to the thing that we can actually measure more directly, which is the current. So to reiterate a point that I made earlier, if you have a conductor which is in equilibrium, you have a total internal field of 0. So there's no internal electric field for a conductor at equilibrium. However, if you do apply a current to the conductor, for example, if you hook it up to a battery so that there's a voltage drop across the conductor, then you're no longer really in the electrostatic regime because all of your charges are now moving. And basically, the reason why they're all moving is because you've applied this field to the conductor. So you get some drift velocity. For the electrons, it's opposite direction of the field. For the holes, it's the same direction as the field. And this drift velocity is basically being caused by this applied electric field. And I want to introduce now a new quantity called the current density, J. And this is something that is, we did fine without it. So what current density is that it is the current per unit cross-sectional area. So if this wire has a cross-section of A and it has a total current of I, then the current density is I over A. So usually in a conductor, it's pretty uniform. In any case, you may or may not have noticed it at this point. We actually made use of the current density earlier in this little lecture because the current density J is in fact the density of the particles per unit volume times the charge of each individual charge carrier times the drift velocity. So notice that this equation right here looks a lot like the equation that I had earlier for the total current. If we scroll back up to the total current, you can see NQVDA. If you divide this equation by A, you're dividing this side by A, you should get J, the current density, NQVD. And so the current density also is a vector, and it's in the same direction as the drift velocity in this case. So before moving on to talk about circuits, I want to go through a few short examples of what we've discussed so far. For the first question, we have that a certain strand of wire has 0.5 coulombs of charge flow through it every 10 seconds. And the question is, what is the average current of this wire? So this would represent I, this would represent delta Q, this would represent delta T. And so the average current is going to be delta Q over delta T. And that is by definition. And so we have 0.500 coulombs divided by 10.0 seconds, or 0.05 coulombs per second. This is 0.05 milliamps, 0.05 amps, which would be 50.0 milliamps. All right, for our second example, we have that we're looking for the current in the wire again. So again, this is I, and we're given the average drift speed of the particles. V drift is approximately 5.6 times 10 to the minus 4 meters per second, because we're given the speed in millimeters per second. And then we're given a length density of 0.25 coulombs per meter. I'm going to call this lambda. And lambda, as you know, is basically represents charge per unit length. So this would represent Q over L. Now, Q, in turn, is going to be the number of charges times the amount of charge on each of these charge carriers. So if you combine these two together, you get that lambda is equal to N times Q over L. Now what I'm going to do is I'm going to go ahead and multiply this by and divide it by an area. So this is what might be called a clever version of 1. I'm multiplying by a clever version of 1. And what that gets us is N times Q times A divided by L times A. And L times A, length times area, is by definition volume. So put all this together, and what you have is that lambda is equal to Q times N over V times the area. Well, N over V by definition is little n, because little n is the number of charge carriers per unit volume, and that's what the N and the V represent, is number of charge carriers and volume. So in other words, lambda is equal to Q times N times A. And the current from the equation that we had before was basically given by Q times N times A times the drift speed. So therefore that's going to be equal to lambda times the drift speed. So we have 0.25 coulombs per meter, and that gets multiplied by the drift speed of 5.6 times 10 to the minus 4 meters per second. So basically we want a quarter of this number. So that gives us that the current should be something like 1.4 times 10 to the minus 4 meters per second times coulombs per meter. You can see that the meters part is cancels, and so this is basically 1.4 times 10 to the minus 4 amps, or 140 microamps. Okay, for our third question, we have what is the drift speed that we would need to create a current of 1 amp in a certain synchrotron accelerator which accelerates clusters of 10 to the 10 alpha particles. Maybe I should draw a rough diagram of what that would look like, by the way. Synchrotrons, although not of this size, are in fact a very useful type of particle accelerator. They are used experimentally in medical physics, for example. So basically what happens here is we have a cluster of charges, 10 to the 10 alpha particles, and the fields are such that this thing basically makes loops around, sort of runs laps around this chamber. And what we're wanting is a current of 1 amp. So here is the cross-section that we might care about. And we basically need this thing to pass through this cross-section enough times that we can generate this 1 amp. And by the way, this is sort of an average. It's sort of assumed average. You can see here where the current density that I mentioned on an earlier slide is not uniform here, because you have basically all the charges concentrated here, yet somehow we can get a sort of average current around the synchrotron. So the average current I is delta Q over delta T. If we want it to be 1.0 amp, which is what the problem is stating, then the implication is that delta Q equals 1 coulomb per second. So that basically means that this thing has to move rapidly enough around this synchrotron such that 1 coulomb's worth of charge passes through this point, or this really cross section. It's represented as a line here. It may be actually a circle if you looked at it face on, every second. So how many charge is in this cluster? Well, Q for the cluster is equal to 10 to the 10 alphas times, basically what an alpha particle is a helium nucleus stripped off all its electrons. So it's basically 2 protons and 2 neutrons. So this is basically 2 times 1.602 by 10 to the minus 19 coulombs per alpha. So the total charge then is going to be about 3.204 times 10 to the minus 9 coulombs. So what that tells us is that if we want to get a total average current of 1 amp, we would need this thing to make many laps, roughly 10 to the 9 laps around this synchrotron in 1 second. So what does that look like? Basically, you need delta Q is equal to 1.00 coulomb, and we can say the number of laps, we'll call it in lap. I'm going to just write it like this. It's going to be defined as this charge divided by this charge. So it's going to be delta Q over Q cluster. That tells us how many times the cluster has to go through this point in order to get this charge in a second, or in any amount of time. So what does this look like? Well, this is basically 3.12 times 10 to the 8 laps. And this has to happen per second. So the drift speed itself, Vd, you basically can use basically a tangential speed. And the tangential speed, you'll recall, is basically going to be given by omega times r, where r was given in the problem. It is 1.5 kilometers, so r is approximately 1,500 meters. And omega is going to be this times 2 pi. So Vd is equal to 2 pi times the r, which is 1,500 meters, times 3.12 by 10 to the 8 meters. And all of this happens per second. Oops, this is not meters. This is just 3.12 laps. So the total drift velocity that we come up with for this, therefore, is about 2.94157. So 2.94 times 10 to the 12 meters per second. So here's the thing about this speed that we just obtained. The universal speed limit, meaning the speed limit that you can't accelerate a particle to exceed by the known laws of physics, specifically by Einstein's relativity theory, is the speed of light in a vacuum, 2.997 dot 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 times 10 to the 8 meters per second. So in other words, it's not possible with this configuration to generate 1.0 amps of average current. We can continue this example though by asking, and makes it kind of a longer example, but we could ask, how many alpha particles would we need to have in this synchrotron, assuming that maybe we'll pretend like we're putting them in clusters of 10 to the 10. How many of these clusters do we need to have in this synchrotron in order to get that current of 1 amp? Well, this is the speed that we'd need for one. This is the maximum speed we can have. So let's assume that we can accelerate to, let's say, 2.99. So we're basically going to truncate this speed off at 2.99 times 10 to the 8 meters per second. That's allowable. That would be a very, very, very high speed particle. Obviously, we're well over 0.99 times c here. So this would take quite a bit of energy to do, but let's say that we can do that. That's the point of a particle accelerator, is to get these at very high energy, very high speed. Then the number of clusters basically would represent this speed. We'll use this as V actual. You'd use V drift for 1, that would be this guy, divided by V actual, and that tells you how many clusters you need to have. So this becomes 2.94 times 10 to the 12 meters per second, divided by 2.99 times 10 to the 8 meters per second. So what does that look like? Well, if you divide 2.94 by 2.99, you get 0.9838. So this is basically 9.84 times 10 to the 3. So you'd have to have 9,840 of these alpha particles in order to attain a current of 1 amp under this set of restrictions. Okay, so now I want to begin what might be the brief introduction to circuits. Of course, we'll go in more depth on circuits in a future lecture set. But you could think of a circuit as a closed loop around which current circulates. So this right here shows a circuit. This is what the circuit might look like in real life. Here's what the circuit looks like as drawn on a diagram. So you have a battery, that would be these guys. You have some wire from the battery, that's usually represented as just a simple line. Here's the wire from the batteries. It's passing through an ammeter. The ammeter in this case actually is what measures current. Then it goes through a light bulb, which should light up as this thing. And at the same time you're measuring voltage. You'll notice that the ammeter is in series with the bulb. The voltmeter is in parallel with the bulb. The ammeter actually, you could say, is also in series with the voltmeter. It's really in series with this combination. And that, by the way, is the correct way to hook up both the ammeter and the voltmeter. Ammeter should be in series with the thing whose current you're trying to measure, voltmeter in parallel. We'll talk more about that in a future lecture. So this is a closed circuit. A charge, an electron for example, could move from right here, the negative terminal, all the way around this circuit and make it to the positive terminal. A hole could come off of this positive terminal, make it all the way around, and make it back to this negative terminal. That means that you could have current actually flowing in the wire. This is therefore a closed circuit. There's also an open circuit. that would be, for example, if you removed one of these wires, or if you placed a switch and you opened the switch. You usually represent that by having a little line sticking off of the circuit. So on a diagram, that basically looks like this. So it's an open circuit now because there's no way for charges to get from here to here. A switch, by the way, you usually draw by having something like this. It almost looks like if you've ever looked at a diagram of a floor plan for a house. You can draw it looking sort of like how you draw a door in those diagrams. And in a sense, that's what it is. If you close this switch, then this circuit is complete and current can flow. If you open it like this, the circuit is not complete, and so you cannot have current flowing through here, and in fact, you'll reach what's called the equilibrium condition for this conductor. Over here, what that would look like, by the way, is if you basically were to remove one of the wires, like so. Now we actually have a open circuit here. Charge will not flow here, the light will not light up. If we close the circuit like so and allow light to flow, or current to flow, then it'll eventually go through the light bulb and the light bulb will light up like so. And these things will have readings that are non-zero. If you open the circuit, then what happens is the light bulb will not be lit up. This will be open, and these things right here will actually read 0 volts and 0 amps. So this thing will look something like this: 0 and 0. So let's get back to those rules for measuring current and potential. Conservation of energy requires that the total voltage drop across each branch in a circuit be equal. And it also requires that the sum of the voltage drops across the individual elements of a branch must equal the total voltage drop for that branch. We talked about this in the last set of lectures in the context of capacitors. If we go up a slide, then what that's basically saying is conservation of energy implies that if this has a voltage drop of some amount, let's say 10 volts, then the voltage drop across the ammeter plus the voltage drop across the bulb has to equal -10. And the voltage drop across the ammeter and the voltage drop across the voltmeter also has to be 10. And the other rule, which you can see comes from this rule, would be that the voltage drop across the bulb and the voltage drop across the voltmeter must be equal. Hence, the voltmeter is placed in parallel with the thing that it's trying to measure, because it will therefore have the same voltage drop as the thing it's measuring, which is what we need. Conservation of charge says that the total charge into a junction must equal the total charge out of the junction. So that means that the total current in each element of a branch must be the same as all other elements in that branch, and the total current into a junction must be divided into the individual branches from that junction. So you have current, here's a junction, some current goes this way, some current goes this way. Here's another junction, this current and this current must recombine and then go this way through the ammeter. Alright, so you can see that the ammeter, since it's in series with these two things, is measuring whatever the total current being drawn by the pair is, because the same amount of current that goes in has to come back out. If we ignore the voltmeter, you can see that the total current would be, there's no junction here, therefore. The total current gets to here, goes through, keeps going, goes through. Same current here as here. So one of the rules, therefore, that goes into designing ammeters and voltmeters is that the voltmeter needs to have a very large internal resistance. The ammeter needs a very small internal resistance. And we'll come back to that point when we talk about Ohm's law, which is actually the second part of this lecture set. So I want to go through one longer example, which is the drift speed in a light bulb. And so let's see that. We have a 12 gauge copper wire. The gauge basically tells us what the diameter is. You can find a gauge chart somewhere and it'll tell you 12 gauges means diameter 2.053 millimeters. The density of copper, by the way, 8.80 times 10 to the 3 kilograms per cubic meter. And we need this to carry 10 milliamps. We're going to assume here that each copper atom can contribute 1 electron. And so what we want to know is what's the typical drift speed of the electrons in this wire. And the hints that we need to answer this are that Avogadro's number tells us how many atoms per mole there are, and the molar mass tells us how many grams per mole. Alright, so to answer this, basically we can use that the drift speed is related to the current using I equals Q little n V drift A. So where do we get each of those terms from? Well, looking end on for the wire, here's the end of the wire. It has a radius of R. It has a diameter of D. The area of this wire must be pi r squared, which is the same as pi times D over 2 squared. D is given. It is basically 2.053 millimeters, or 2.053 times 10 to the minus 3 meters. Alright, so we've got that. The thing we're actually trying to solve for is the drift speed. So we could rewrite this by saying V drift is I over N times Q times A, for what that's worth. So Q is charge of an electron. Q is about 1.602 times 10 to the minus 19 coulombs per electron. So what we need to do at this point is figure out the value of N, where N is again defined as the number of charges per unit volume. So how are we going to do that? Well, we've been given rho, the density, so that is mass per unit volume, and that is given in this case as 8.80 times 10 to the 3 kilograms per cubic meter. Okay, so if we have that, then our hope basically is to try and figure out how many electrons are per cubic meter, because that will give us little n. Well, what we need to know is how many free electrons are there in this much copper. In other words, in 8,800 kilograms of copper, how many free electrons do we expect to have? And the answer is that in 1 mole, there are 63.54 grams. So this is the molar mass. I like to use big M to represent that. And this is 63.54 grams per mole, which is 0.06354 kilograms per mole. Second thing is that we have we have the Avogadro's number, 6.022 times 10 to the 23 atoms per mole. So this is how many atoms do we find in a mole. This is how many kilograms do we find in a mole. And of course, last but not least, we have 1 electron per atom. So if we combine these three numbers, really if we combine these 4 numbers, we get the number of electrons per unit volume. So what I'm basically doing is, let's call this one N sub E for lack of a better word, or N sub F E, free electrons. So N is going to be rho times M times the Avogadro's number times the number of free electrons. This one, of course, is 1, but it gets us to the units we need. So that means that N is going to be 8,800 kilograms per cubic meter times, basically, really we need to be dividing by the molar mass. So I put that in the wrong place. Really, we should have it over M like this. So times Avogadro's number, which is 6.022 by 10 to the 23 moles per atom, and then times 1 electron per atom. So then that is going to be divided by the molar mass of 0.06354 kilograms per mole. Oops, this is backwards. This should say atom per mole. This one right here is E minus per atom. So the units will all cancel in such a way that you end up with electrons per cubic meter. You can see that there's kilograms here and there's kilograms here. You can see that there are per atom here and there's atoms here. And you can see that there are moles here, or per moles here, and there's per moles here. So everything cancels except for the number of electrons and the per cubic meter, which is the things that we want. So this means that N is going to be given by approximately 8.34019 ... So call that 8.34, and that's of course times 10 to the 23 plus 5 is 28. So that's how many electrons per kilogram we're going to have. Okay, so now we can combine all of this information, which we'll do up here where I've got some space to work in. And what you end up with is that the drift speed needs to be, I was 10.0 milliamps. So that's 1.00 times 10 to the minus 2 amps. You've got to divide that by N, which was 8.34 times 10 to the 28 electrons per, not kilogram, it's per meter cubed. And then that should be times the charge of an electron, 1.60 by 10 to the minus 19 coulombs per electron. And then we also have to multiply by the area, which is basically going to be pi times 2.053 by 10 to the minus 3 divided by 2 quantity squared. So we got to throw all that into our calculator. And this right here is meters. So throw all of that into our calculator, and what we're going to end up with is, by the time all is said and done, we end up getting a drift speed of about 2.26 times 10 to the minus 7 meters per second, which is very lethargically slow if you think about it. But it's because there are so many electrons being contributed to all of this that we are able to do it this way. So you can have a very small drift speed, but because there are a large number of electrons, even compared to the charge itself, you end up with a pretty large, as a result, current. 1 amp is a fairly large current, by the way. So to give a brief summary of what all we've covered in this lecture, I've introduced the concept of current, which is the flow rate of charge through a given cross-section. Average current is delta Q over delta T. The drift velocity, in turn, is the average velocity of a particle over a period of time after it's made many collisions. That's represented by a Vd. You can get from drift velocity back to current via this equation. I is Q in A Vd, where Q is the charge of each carrier, N is the density, that is the number of charge carriers per unit volume, A is the cross-sectional area that this is taking place through, and Vd is the drift speed. The current density, in turn, is the current per unit cross-section area. So take this equation and divide by an A, and you get this equation. This works out very nicely if you have a uniform current density. However, there are cases in which you might not have a uniform current density, in which case you can basically sum over all the individual current densities to get the total current. You're basically summing them by multiplying a segment of space, the current density for that segment, times the cross-sectional area of that segment of space. And last but not least, a circuit is a closed loop through which current circulates. So that's all that I have for today's video. This is the first part of this lecture set. It's actually a two-part set. So we'll have the second part in a future video. In the meantime, thanks for watching, and I hope you found this helpful.